Good day and welcome back for part 4 of the discussion on the fundamental theorem of calculus. In our previous videos, we've introduced both parts of the fundamental theorem of calculus and explored several examples. In this video, I'd like to remind you of the key properties from the fundamental theorem of calculus and then look at a few additional examples. The fundamental theorem of calculus does have an overall hypothesis. We need to be dealing with a continuous function on that closed interval from a to b. And then if that is the case, the first part can be written most conveniently as the derivative of the definite integral from a to x of f of t dt is simply equal to f of x. That is to say, that upper limit of integration x is substituted in for t. Also note we saw a variation of this as well. Instead of integrating up to a function of x, we could write this in a more general form. The definite integral from a to a function of x, it's now a composition. We approach it in the same way, we just remember we need to use the chain rule. So that u of x gets substituted in for each and every t to make this f of u of x. And then by the chain rule, we multiply by u prime of x. And the key thing to make sure you remember is that u prime of x. Forgetting it is a very common mistake. The second part of the fundamental theorem of calculus allows us to quickly and efficiently evaluate definite integrals when we know an antiderivative of little f. So if big F is any antiderivative of little f, and remember what that means. The derivative of big F is equal to little f. Then that definite integral is simply big F of b minus big F of a. And oftentimes for convenience, we will write this first as big F of x evaluated from a to b. So let's illustrate these concepts. In the first example, note, we're not precisely in this desired form. In order to use the first part of the fundamental theorem of calculus, we want the integral we're differentiating to go from a constant to a function of x. So we need to flip this order. But remember, when we flip the order, we introduce a negative sign. The negative is a constant which we can pull in front of the derivative. But once we've made this minor modification, we are good to go. Following our template above, we take cosine x, we substitute it in for each of the t's so that we have f of cosine of x, and then we multiply it by the derivative of cosine. So 1 over cosine squared plus cosine times the derivative of cosine, which is minus sine. And you most certainly could do a bit of arithmetic to simplify, but I'm going to leave it precisely in this form. Our second example to get us going involves evaluating a definite integral. As long as we can recall an antiderivative of sine, we are good to go. So can you think of a function whose derivative is sine? And an antiderivative of sine is minus cosine x. And if you're unsure of your antiderivative, you can always double check. Note that the derivative of minus cosine, you have the minus sign, which comes out of the derivative, multiplied by the derivative of cosine, which is minus sine. The minus cancel each other off, and we're left with just the sign. Now we substitute in that upper limit, pi over 3, and then we subtract away what we get when we substitute in that lower limit of 0. And recall, whenever you're in this position of trig functions, common values, we need to take it one step further. So cosine of 0 is the number 1. Cosine pi over 3 is what number? 1/2. So this becomes minus 1/2 minus a minus 1. So simply 1/2. And it is now time for you to do a bit of practice. For the fundamental theorem of calculus, you can find an associated worksheet in Canvas. What I would like to ask you to do, if you haven't done so already, is to give yourself some significant time to work through it, at least 20 minutes, and see what type of progress you can make. Then come back to this video where we'll go over a couple of the examples, and then you can also find full solutions posted on Canvas as well. So once again, pause the video, give yourself some time, work on the worksheet. So hopefully you had a chance to pull up the worksheet and work through a few of the problems. I would like to go over problems 2A and C from the worksheet, and note the solutions to other problems can be found in Canvas. The reason I chose 2A and C is that the second part of the fundamental theorem of calculus, which we use to evaluate definite integrals, is a property that I think I can safely say we will use hundreds of times throughout the calculus sequence. So let's begin with the first one. And in order to evaluate this, note, as we've seen previously, sometimes we may need to algebraically manipulate to get this into the position where we can use those common anti-differentiation formulas. And the key manipulation in this case is to realize that x plus the square root of x is really x to the 3/2, because the square root of x is x to the 1/2. So in order to anti-differentiate each of these terms, we need to think of our common formulas. X to the 3/2 is good to go. We can anti-differentiate using this kind of opposite of the power rule. And let me give you a quick reminder to the side in terms of our common antiderivatives, and we will have some more convenient notation that we introduce in our next section. If f is the little f is x to the n, an antiderivative would be 1 over n plus 1 x to the n plus 1, as long as n is not equal to minus 1. And note that would be what? N equals 3/2 with the second term, but the first term, a constant, also fits this pattern. This would be n equals 0, if we prefer to think about it that way. So note, when n is equal to 0, you would get back 1 over 0 plus 1, x to the 0 plus 1. And I know that looks rather abstract, but we're saying the antiderivative of 1 is x, and this makes perfect sense. The derivative of x is 1, and furthermore, if you differentiate a constant times x, we always get back that constant. And this is an anti-differentiation formula we will encounter frequently. So applying that, in words, the antiderivative of any constant, such as 3, is that constant times x. To anti-differentiate x to the 3/2, we know 3/2 plus 1 is 5/2. 1 over 5/2 is 2/5. And hopefully as you've worked through and evaluated more and more of these, you become quicker and more efficient at each step of the process. We now simply substitute in 1, put a minus sign, plug in 0. So we would have 3 plus 2/5 when we substitute in 1, minus sign we substitute in 0. 3 plus 2/5, if you want to combine it, that's 17/5, but you could certainly leave it one step shy of this. In problem 2C, we need to do a very similar approach. And if you have not already completed this problem, pause the video, give yourself, I don't know, maybe 90 seconds, 2 minutes, and evaluate this definite integral. In order for us to use our common anti-differentiation formulas, namely this one that undoes the power rule, we need to first algebraically manipulate. We can break this up into 2 fractions and write it as x to the 4th over x squared plus 1 over x squared. And now individually, similar to what we saw above, we can anti-differentiate each of these terms. So in the first one, n is equal to 2, So this would be 1/3 x cubed. And for the second term, x to the minus 2, we're using this formula with n equals minus 2. So we have to be a little bit careful with minus signs, so I'm going to write out the details. 1 over minus 2 plus 1, x to the minus 2 plus 1, from 1 to 2. And just note, so there's no confusion, x to the minus 1 is 1 over x. And minus 2 plus 1 is minus 1. So this is written slightly more conveniently as 1/3 x cubed minus 1 over x. So we substitute in x equals 2. Minus sign, we substitute in x equals 1. And I would leave it precisely in this form. If you want to do a little bit of arithmetic, you're certainly more than welcome to, and it will become 17 over 6. This finishes our discussion of the fundamental theorem of calculus, but hopefully, as I've indicated throughout our discussion, especially part 2 is going to be an extremely important property we make frequent use of throughout the remainder of the course. So it is in your best interest to spend some time, work suggested problems, and master this fundamental theorem of calculus now, so that when it becomes a smaller part of a larger problem, you will be good to go. So if you have questions, do not hesitate to reach out. Stay tuned. Take care.